In this session, let us have an introduction to DC machine. Basically, DC machine we will not use because of commutator. Okay, of course DC machines we use as a feedback path of control system, but to handle bulk of power. Okay, DC machine, like normally we don't use, except like if I have alternator. Okay, in order to excite the alternator as an exciter, like we have to excite the alternator with the DC, so there you can find DC generator. Okay, except that most of the times DC machine will not be used. Okay, because of only one thing, that is commutator. All problems of DC machine will lead you to commutator only. Okay, it means in this session we will introduce like what are the problems associated with DC machines and all. Anyway, fundamentally, if I see, these are the two poles. Okay, so in these two poles, in between, let me have a coil and let me rotate the coil. And for example, each coil side is connected to one slip ring. Okay, so these are going to be slip rings. Okay, fundamentally induced voltage is going to be AC only. That AC will be converted into DC by commutator. So for example, if I think of slip rings, it is not split ring or commutator, it is normal AC machine. For example, if I keep my poles in the stator and if I rotate the coil in the rotor, then what will happen? At one instant it is under N pole. For example, you are sitting on this conductor and this conductor name is X and this conductor name is Y. Okay, so as of now X is under the N pole region. Okay, for example, induced voltage here is dot here, induced voltage here is cross here. Okay, because it is under N pole and it is under S pole, so induced voltage is in this direction because dot it is coming out, and induced voltage is in this direction. Okay, such that what will happen, as of now, for example, if you think of this as dot as positive, so as of now positive maximum induced voltage will be there because it is under the N pole at the center of the pole. After that, once it start rotating, it will reach to MNA or magnetic neutral axis, or like zero flux density, then zero induced voltage will be there. And after that, this X conductor, once it reach to the S pole region, automatically induced voltage will be reversed. Okay, so if you tap that through slip rings, and to the slip rings if you keep the brush, so if you sit on each conductor, induced voltage is sinusoid, so automatically across slip rings also induced voltage is going to be sinusoid, or at least AC we can say. Okay, now let us come to DC machine. Actually this is AC machine. Okay, so if I think of DC machine, what will happen in DC machine? We are going to have a split ring here. Split ring here. Okay, so what is split ring? Very simple. This is going to be copper ring only. So in the copper ring, I'm going to keep insulation here. I'm going to keep insulation here. Okay, so from here to here it is a copper ring. Here to here it's a copper ring. In between those two, we are going to provide insulation. For example, this is the ring. Okay, so across this, here insulation will be there, here insulation will be there. From here to here copper ring, from here to here copper ring, here to here copper ring. In between those two half of the copper rings, let me have electrical insulation. Then let us see what will happen. Okay, for example, if it is rotating, automatically, because it is on the same shaft, it also will rotate. Okay, so for example, you are sitting on this conductor. As of now, dot is the induced voltage. As of now, cross is going to be the induced voltage here. Means that my induced voltage is going to be in this direction. My induced voltage is going to be in this direction. Okay, such that my induced voltage in this direction plus this direction is going to be 2 times. Okay, so for example, this is conductor X. This is conductor Y. Now you are sitting on conductor X only. For example, as of now it is under N pole. After half of the rotation, zero flux density. Again after half of the rotation, it's going to be under S pole. Such that if you sit on conductor X, my induced voltage is going to be alternating. But the advantage of split ring is, for example, along with the conductor, this also will rotate. Okay, for example, as of now induced voltage is in this direction, so this is connected to this part. Let me think of this as plus because induced voltage is coming out and induced voltage is going in, so it is going to be minus. Okay, such that my currents are going to be from here, here in this direction. So from plus, induced voltage will be tapped here across this particular ring, half of the ring, and after that induced voltage or current will flow in this direction. For example, after 180 degrees rotation, what will happen? Let me rotate this by 180 degrees. After that, Y conductor will be placed here, X conductor will be placed there. So this is going to be conductor Y, this is going to be conductor X after half of the revolution. Okay, so under N pole, focused here all of you, under N pole, which type of induced voltage will be there? Dot. So under N pole region it is going to be dot, under S pole region it is going to be cross, same as before. Okay, so the moment conductor is coming in the region of N pole, induced voltage is dot. The moment conductor is going to the S pole region, induced voltage is going to be cross. Now what will happen? Means this is in this direction induced voltage, this is in this direction induced voltage, this induced voltage plus this induced voltage is going to be this induced voltage. Now in our previous section, for example, this is A half ring and this is going to be B half ring. Okay, so because of this rotation, it also will be rotated. No, the moment it rotate, A will come to here, A will come to here, B will come to here. Okay, now if you consider induced voltage and currents flowing, now here from here induced voltage is in this direction, so again this is going to be plus only, this is going to be minus only. From here currents will flow in the same direction. Okay, so the advantage of split ring is, though internally, for example, if you are sitting on X conductor, in X conductor induced voltage is dot here, in X conductor induced voltage is going to be cross here. Okay, so induced voltages are going to be alternating. Okay, so but still after split ring, my induced voltages are going to become DC. Okay, so because of my commutator, AC induced voltage internally is becoming converted into DC, and beyond this nothing is required. Okay, so for gate or ES, beyond this nothing is required. Don't think much about winding diagrams, wave winding, lap winding, simplex wave, duplex wave, like progressive winding, retrogressive winding. There will be so many windings, like so those things are not at all required. But what is required from interview point of view or from concept point of view, what is required, let us discuss. Okay, for example, is it possible to have, means if I want to break the connection, is it possible to break the connection without spark? Not possible, because for example these two are the two terminals. Okay, so I am about to close the switch here, for example across these two I have 100 volts. Okay, so across these two I have 100 volts, so the moment 100 volts across these two 100 volts is there, I am about to close the switch. Now what is dielectric strength of air? 30 kV per centimeter. For example, in between these two 1 centimeter is the distance. Okay, so in between these two 1 centimeter is the distance. In that, what is dielectric strength of the air? 30 kV per centimeter. So up to 30 kV, my air can block the voltage. But what is the applied voltage across these two terminals is going to be 100 volts only, so nothing will happen. But you are about to close the switch. So 1 centimeter will become half centimeter. Half centimeter 15 kV is sufficient. Maybe it will become 1 mm. 1 mm in the sense just 3 kV is sufficient. So you are about to close the switch. So at one instant, this particular 100 volts is sufficient to strike the spark. So conclusion is very simple. What is that? Means without spark we cannot make or break the contact. Okay. So for example, coming to here, because all problems lead you to commutator only. All problems of DC machine will lead you to commutator. For example, you are sitting here on the brush. So brushes are going to be stationary and this split ring or commutator is going to be rotating. Now this brush is in contact with A. Okay, after that, after half cycle revolution, this contact or this brush should be in contact with B. So means across these two brushes, AB, in between insulation is there. So this is going to be the insulation. Okay, so what will happen? So for example, if this is the brush, okay, this is half of the ring, so it will be in touch with it. Once half of the ring is over, it has to break the contact with A and it has to initiate the contact with B. So spark is going to be continuous phenomena in DC machine. Okay, so because of spark, what are the disadvantages? Let us see. Okay, so what is spark? Spark is nothing but current flow through air. Okay, so means because of this continuous sparking, air around the commutator will be ionized. Okay, so the moment it is ionized, dielectric strength of the air is going to be reduced. For example, during what do you say? Let me tell you, during rainy season, Okay, so during rainy season, normally lightning strokes will be there. Why? Because during rainy season, dielectric strength of the air will be reduced such that lightning strokes can happen. Okay, so similarly here also, because of this ionization of air, dielectric strength around the commutator will be reduced. Okay, so the moment dielectric strength around the commutator is reduced, then what has to be done? Across these two, we cannot maintain, in the sense across adjacent commutator segments, we cannot maintain more than 20-25 volts. Okay, so the moment across each commutator segment voltage cannot be 20-25 volts, then automatically output voltage cannot be in kVs, kilovolts and all. Okay, so for example, if you think of alternator, what is normally output voltage of alternator? Roughly 11 kV we can say, but 11 kV is the biggest thing which is impossible in DC machine because of commutator, because of air ionization and all. Okay, so DC machine voltage can be 100 volts, fine, 200 volts, fine, 500 volts, too much. Okay, so more than 1000 volts normally you don't find DC machine at all. So maximum voltage, in this output voltage, cannot be more because of commutator, one thing. Now let us think of second thing. What is second thing? For example, in our synchronous machines we have seen, is it better to keep the armature in stator or rotor? Stator. Okay, because if you think of rotor, mechanical stress will be more centrifugal, because of centrifugal forces. The moment mechanical stress is more, what you have to do? You cannot use low quality insulation, but rather hard composition materials has to be used like asbestos, mica and PVC and all. Okay, so means here, for example, in DC machine, what is commutator? It's a mechanical rectifier. So mechanically you have to rotate the rotor in order to get DC voltage. Gun case. Okay, so in DC machine, armature should be in the rotor only. There is no other go because of commutator. So the moment armature should be there in the rotor, centrifugal forces will be there, hard composition material will be there. So because of that, cost of the DC machine is going to be more. Okay, now for example, okay, let us think of, this is going to be ring winding. Okay, basically let me tell you, in three-phase AC machine, my winding can be either open or closed. For example, if you think of star connection, is it open winding or closed winding? Open. But still, though winding is open, if it is delta connected, it will be closed winding. But in AC machine, I can have open winding also. Why? The advantage is IA plus IB plus IC equal to 0 at any instant of time. We discussed in our previous sessions. Okay, now coming to here, DC machine, why we should have closed winding only, why can't we have open winding? Okay, for example, in order to discuss that, let me take ring winding. Okay, so in ring winding, for example, if you think of sinusoidal flux density distribution here, basically in alternator we struggled a lot to keep my flux density wave better sinusoid. Okay, we tried our level best to keep the sinusoidal flux density wave from operating flux, and after that, in order to have better induced voltage, better sinusoid induced voltage, we we spent more money for KP KD. Okay, so because of pitch factor and distribution factor, my number of turns to be provided for in order to produce rated voltage is going to be increased or not. Okay, so because of that, volume of copper is increased or not, means that we are investing more money or not? Yes, but still we invested more money in synchronous machine in order to make flux more sinusoidal and in order to make induced voltage more sinusoidal. But here what will happen, let us see. For example, if I think of sinusoidal flux density wave here, okay, so sinusoidal flux density wave, so this is going to be flux density. From here, let me rotate myself theta. So with respect to theta, if I have sinusoidal flux density wave, what will happen? Let us see. Okay, basically if I think of sinusoidal flux density wave, for example, my induced voltage in a conductor directly proportional to flux density. If flux density is more, induced voltage will be more. If flux density is less, induced voltage is going to be less. For example, here induced voltage is 10 volts. For example, because of sinusoidal flux density. So, because of flux density, maximum flux density, induced voltage is going to be 10 volts. For example, now it is at 45 degrees, right? So, sin 45 is 0.707. So, if I think of here, if it is 10 volts and if I have sinusoidal flux density distribution, induced voltage here is going to be 7.07 volts. and induced voltage here is going to be 7.07 volts. And of course here it is going to be minus 10 volts, minus 7.07 volts, minus 7.07 volts. Okay, now there will be two things here. In our DC machine, why flux density waveform is intentionally flat topped, I'll tell you. And second thing is, why my brushes should be in the MNA only, not anywhere else. Okay, for example, if I keep my brushes here, if you see here, like from here, okay, so this induced voltage, this, and through this, and through this are connected in series or not? Yes. So this are connected in series, this are connected in series. Okay, so these induced voltages and these induced voltages are same, of course negated. Okay, so means see here from the brush through the commutator, this induced voltage is going to be series connected or not? Yes. So under N pole region, all the coils are series connected. Under S pole region, all the conductors are under series connection. And in between here, if I keep brush, okay. So how much will be the output voltage across the brush? Output voltage is going to be 10 volts plus 7.07 plus 7.07. So roughly 14 volts plus 10 volts, roughly 24 volts will be there. Okay, so in the upper portion and lower portion, these two are parallelly connected. So these are all connected in series, I'm going to have two parallel paths. Induced voltage is going to be 24 volts. Okay, for example, if I have IA armature current after the brush, this half should give you IA by 2, because these are all connected in parallel. This half should give you IA by 2, because these two are connected in parallel. So IA by 2 plus IA by 2 is going to be IA. Okay, for example, rather than having sinusoidal flux density, if I can have flat topped flux density, okay, so if I can have flat topped flux density, what is the advantage? Let us see. For example, peak value of sinusoid and peak value of flat topped is same. Okay, so at here, induced voltage is 10 volts. Because peak is same. But if you think of, for example, with respect to 45 degrees here, okay, how much will be the, because if it is maximum flux density, because of flat toppedness here, almost maximum is only coming flux density. So here, for example, this is 9 volts. Okay, so here, for example, 9 volts. Because flux density is increased or not compared to sinusoid. So 9 plus 9, 18 plus 10 means my output voltage is going to be 28 volts. Okay, so compared to sinusoidal flux density, if I have flat topped flux density, induced voltage is going to be increased or not? Yes. Okay, so which is better? Obviously flat topped is better, because for example, this is going to be my slot, okay, because my conductors has to be placed in the slots, rotor slot, armature slot. So inside my slot is like this. So inside my slot I have to keep conductors, and my slot is going to be iron. Okay, so my core is going to be iron. Inside conductors will be there. They are going to be electrical conductors. In between these conductors and slot, I have to provide insulation or not? Yes. Now insulation, voltage is going to be one of the main design constraints for insulation, right? So for example, for given voltage, these are the conductors, this is the slot, means in between insulation has to be provided. That magnitude of insulation will be decided by voltage or not? Yes. Now that induced voltage will be decided by peak value of flux density. For example, as of now, induced voltage can be 9 volts or 7.70 volts, depending upon sinusoid or flat top. Now, but once you start the rotation, ultimately this particular conductor has to be placed here and here or not, because if it is rotating. Okay, so my insulation, magnitude of insulation to be designed will be decided by peak voltage. Insulation will be decided by peak voltage. Now, for example, for the same 10 volts, if I design the insulation between my slot and windings, now for the same 10 volts design, I can get more voltage here or not? Yes. And we don't have any love or affection towards sinusoid here, because in AC we was having that. Okay, why? Because in AC my induction motor, which is my main customer, so means as induction motor like sinusoid, we have to love sinusoid, there is no other go. But here we don't have any special affection towards sinusoid. So compared to sinusoid, because if I think of sinusoid or flat topped with the same peak flux density, sinusoid or flat topped with the same peak flux density, means magnitude of insulation requirement is same or not? Yes. So for the same magnitude of insulation, for the same stress upon insulation, output voltage is going to be increased or not? So conclusion is very simple. In my DC machine, flux density waveform is intentionally made flat topped. Okay, how to make it flat topped we will see later. Now, coming to the point, always we have to keep the brushes at MNA. Why? Okay, for example, see here, if I keep my brushes across these two, how these three are connected in series, so 9 plus 10 plus 9 is going to be 28, minus 9 minus 10 minus 9 is going to be again 28. So these 28 plus 28 is going to be net 28. So how many parallel paths are there here? 2 parallel paths are there. For example, if I want to have open winding, okay, not closed winding, but in DC machine, if I try to have open winding, what will happen? For example, see here, if I open circuit here, okay, then through this IA by A will flow, through this current cannot flow. Okay, so how much will be the net magnitude of current? Is going to be one parallel path only. So whenever you are taking current from this parallel path is not doing any work. So underutilization of materials used in the design will happen, because upper portion I invested my volume of copper, but that particular copper is not being utilized because it is not sending many current. Okay, so for example, if it is rotating in this direction, this particular open circuit after some time will occupy this portion. So under that condition, lower portion of conductors will not be utilized, upper portion will be utilized. So point here is very simple. What is that? At any cost, we should not use open winding, rather we have to use closed winding only in DC machine. So the moment it's closed winding, my volume of copper designed can be completely utilized in DC machine. Okay, so next thing is, for example, if I don't keep the brushes at MNA, okay, magnetic neutral axis, okay, rather than that, for example, if I keep my brushes here, okay, then if I keep my brushes here, we know that induced voltage in the center, induced voltage in this coil, already we made 10 volts and we made flux density flat topped. So induced voltage here is going to be 9 volts, induced voltage here is going to be 9 volts, induced voltage here is going to be minus 9 volts, induced voltage here is going to be minus 10 volts, induced voltage here is going to be minus 9 volts. Okay, for example, if I make from here to here one parallel path, one parallel path, what is the induced voltage here? See, 10 plus 9 minus 9, output voltage is going to be 10 volts. Okay, because this is going to be 10 parallel path, because parallel path in the sense these three are connected in series, both are connected in parallel. Okay, so minus 9 plus 9 plus 10, minus 9 plus 9 will be cancelled. Here also minus 10 minus 9 plus 9, minus 9 plus 9 will be cancelled, such that output voltage will be 10 volts only. So logic is very simple. What is that? For example, if I think of here, my conductors are going to be, okay, so this is going to be 9 volts, 10 volts, 9 volts, such that output voltage is 28 volts. Okay, now in other direction, minus 9, in opposite direction it also will be 9 volts, 10 volts, 9 volts. But if you think of here it will be minus 9, minus 9. So minus 9 plus 9 will be cancelled and 10 will come. Minus 9 plus 9 will be cancelled and 10 will come. So in order to have maximum output voltage across the brushes, there are two things. What are those two things? What are those two things? One is going to be like, my brushes should be at MNA, and second is going to be my flux density waveform should be flat topped.